Okay, welcome back class. Now we will see the lab part of chapter number 2. So last time, if you remember, we saw how to load images in the lab part. We saw how to load images in lab 2. The basic operation on the images, how to draw the lines or circle or rectangle or like this. Now this time we will do some basic image processing on the images. So this is the first part of this lab 3. So there will be two parts. So in the first part, what you do is that download this file from the SharePoint, the file ending with IPYNB, and put it on your computer from where you can access. Then you will run the Jupyter, and you should go to the same folder where it is this file is. You cannot run this file directly. You have to run the Jupyter, and from Jupyter you will access it. So when you click on this file, it will open as a separate page. So here it is. This is the page. So start from the top. Always when you start the lab, every time you start the lab, you have to run the code, you have to run the libraries in the beginning one time. So for example, you work today, you will run this library command. When you come next time, for example, you turn off your Jupyter, you go back home. After you turn on your computer again, now you have to run this line again. You have to import the files again. So it is only for one session. Okay. So when I do this over here in this part, we will be doing three things mainly. We will be having some sort of playing with the image. Then we will discuss the different types of noises as we saw in the lecture number 2. And then we will saw the filters. So remember, we begin by importing the three libraries we discussed. The libraries are CV2, NumPy, and Matplotlib. Last class I discussed that in the matplotlib, this command over here, matplotlib dot percent matplotlib is basically a magic command, and what it does is it asks the computer to show the images in the same web page, not as a separate page. There is another command if someone wants to try, that is magic %, matplotlib, then space, and then you can write notebook. In the case of notebook, it will show you also the coordinates of the mouse when you move it on the image. Okay. Other than this, today we will also discuss a little bit. First time we will discuss NumPy, why we use it. So first use of NumPy will come today, and CV2 you already know. So over here, first of all, to use the image, we will be reading the image using cv2.imread, and remember over here this is our constant. The value of this constant is 0, but basically it means that load the image as a grayscale image. Okay, and then in the second command, so this is the command for reading, and then this is the command for displaying. And in the last lecture I clearly told you that we will not use the show command from CV2 because it is more complex, it has some issues. We will use the imshow command from the PLT matplotlib library. Okay, so we gave over here one option, just like we gave option over here about image should be input as grayscale. Similarly, we put over here one command that image should be output or displayed as grayscale. Okay, so the image displays over here like this. So you can see on the sides of the image you will see these numbers. These numbers show the pixel values on both the axes. Okay, so you can clearly feel over here that this image is somewhat around I think a little less than 400, so maybe it is 380 and multiply by 520. So this is just a feeling, not exact value. Okay, so when you save the image inside an image variable, so the variable name is img, you can also display the variable. Over here you see the variable is displayed. Basically img is nothing but a two-dimensional array. So this two-dimensional array will have different values sorted by rows. So over here you see the values that are stored as rows over here. And at the end over here you see the type of the array, which is uint8. It means unsigned integer, and the size of each integer value is 8 bits, which means the value can be from 0 until 2 to the power 7, which is 255, 0 to 255. Then last class we discussed, this was your assignment also, how to slice one part of the image. So this is called as image slicing. Slicing is just like you take an apple, you cut it, that is called the slice of the apple. Similarly, this is the image slicing where we cut one part of the image. So here you see I cut over here this part of the image. So you see one slice from that image. Okay. One more thing that we can use is the image variables in Python. They have a property called as shape. The shape property can be used to show the size of the image. So over here in this case, I can show that image, its shape is stored over here as two values. One is for x direction and one is for y direction. So 0 value is for the y direction. So not this image, this is the slice, the original image. This value is 0 and the other one is 1. So 0 value, the maximum range is 383. You remember just a little bit ago I told you that it will be around 380. And the other value I told that maybe it is 320, so it's not 20, it's 520, but it's little less, it is 513. So shape is basically two values. You can access these two values by the index 0 or 1. Okay. So this property is important. It will always give you a very good help when you want to find the check the shape or the size of the image. Next thing that comes is that how we can access the pixels. So one method that you may have seen in your media computation courses is that you try to select the image pixels one by one in each row. So first of all, you have an outer for loop that will select each row. Okay. And then you have an inner for loop that will select each pixel for that row, inside that row. So row only changes when all the pixels in that row have finished. So it scans like this from left to right, it will keep on going. So here you will see that you have got over here these values like this arranged in a sequence. For example, if I want to see when this sequence finishes for one row, I can just put one more print over here, print, and here I will say like this. So when you run it, you see now it is changed. If I don't want to put a end to start a new line, I can write over here like this. Maybe I put a space. End command says that what should happen when I print. After the printing, should I print a new line, which is by default like this. So here it is. See, first row it prints 255 for the whole row. Then in the second row the values they change. Then this is the third row, and they keep on going like this. Clear? So this was it. This is how you can print the values. Once, so each value is accessed row wise. So you start with the first row, then the second row, third row, like you did if you remember in media computation. These were the things done over there. Now you can use the same two for loops. These are called nested for loops. You can use them to make a negative of the image. If you remember, negative of an image means that image values are inverted. So here is the negative, you see. This is the negative. Negative is created by subtracting the value of the image from 255. So 255 minus the image value, the pixel value. That will make the negative. Clear? So that's how it works. It will make a negative. So here you see, for example, initially the value was 255, now it becomes 0. Clear? It's 2 times negative. Let me run the code again. You see, original value is this one, all zeros, and this is the negative value that happened over here. All the values have become 255 because 255 minus 0 for the first row, it is 255. That's why this is bright white. Clear? So this is the negative, but we normally don't do like this negative. There is one more method to do the negative, which is more simple. Let me show you. I just add one row. You can say over here plt.imshow, and I didn't put it over here, but you can easily write it. Instead of writing 2 for loops, you just write original image. So the problem is that the image is modified here. I shouldn't modify the original image. I should write it, for example, negative image, neg image. It's not good idea that I change it, because every time I will run this code, every time the negative will change back to original. So I run from the top again. This, now it will never make any change. Only one change. Neg image is not defined. So I have to define this image here. I define it first. No. Now it will work. So here I can do like this, I think. Let me check. So it will, at the end of the command, if you put a semicolon, it will hide this extra line that prints on the top. Okay, if I put img, it will show me the original image. If I write 255 minus img, it will show me the negative of them. So effectively in Python, it is so easy that instead of writing these 2 for loops, you don't need those too many things. You just write this 255 minus img. It will automatically subtract the whole image. It will subtract the values from 255. I hope it's clear. So this was a little bit of tweaking just to make you clear. Try to run these commands yourself and try to practice with it by using some other image yourself. The next part of this lab is the noise. So remember, you must have taken the class lecture before coming here. So in the class lecture, we saw that there are 3 main types of noises. There are many types of noises. Practically there are many more, but here we keep them simple. We only study 3 types of noises. So they were salt and pepper noise, impulse noise, and the last one was Gaussian noise. So we will see over here. So first task we do is that we show the original image for the Lina. So Lina is some model which is shown in this book for the noise. So this is the original image. This is for comparison, and then we will compare this original image with the noisy images. So this is original image, and first one over here is the salt and pepper noise. You see here a lot of black and white dots, a lot of them, not less. So first of all, when I load the image, so this command is quite familiar to you, image1 equal to, and this is the image. One thing you should remember, that the image is inside the folder images. That's why I write the complete address, and my file is in this location. So remember, my file is in this folder: courses, computer vision, lab 3, and image processing part 1, this file. So there is a folder in computer vision at this location. It's called images. Inside that folder there is this image. That's why I write this complete address. Okay. Now the interesting thing is that when I want to display an image, image will be in its original size. Whatever size it is, it will display the image. If it's small, it will show it small. If it's large, it will be shown large. I can force the image to be big or to be small. For example, here I show the image. So let me do it. Here first I put the comment. So remember, the hash sign is the comment. This is the original image. The original size is this one. Okay. But I can force the image to become large. So this for your assignment that's coming over there, you will see I have asked some question for this. So make sure you understand this line. So PLT has a command or a function called figure. In this figure, so this figure command allows us to change this figure. So one of the changes I can do to this figure is that I can change its size. I show the size as fixed size equal to, and then I will give the values over here inside the brackets. When I give it inside brackets, it's called tuple. Tuple is a data type in Python. So it is a tuple. The values are in X and Y. So what should be the value in X direction and what should be the size in Y direction? So here it is 12 by 12. So it is quite large, you see over here. So it forces to image to become large. You can select any value you want. For example, you make 12 by 8. It's allowed, no problem. Okay. Now I think the image, sorry, 8, not 18. So now you see it has become changed. I can make it 16 by 8. So it will change the size as you make changes over here. If the changes are not so big, maybe you don't feel it. Okay, sometimes. Here I make it back to 12 by 12, it will become large. Now you see, now it's large. Okay. So fixed size in the figure command, it's important. It will allow you to change the size of the figure. So this was the original image. Next thing we do is that salt and pepper noise is for the same image we produce the noise. Now noise is not something that we want to introduce. It's a natural phenomenon. For example, you have a paper photo, a photo that is printed on a paper, stored somewhere in your house. When the time passes, the dust comes on the image, and there are many other factors. The paper becomes old. Many other factors, they introduce some sort of noise on the paper. So if you scan the image, it can have different types of impurities or noise. So here we see one of the noise, salt and pepper noise, which is mixture of black and white dots, and they are a lot. So here you see there are so many that the original picture is not so clear. Clear? So this is it, that's loaded over here, salt and pepper noise, same size, 12 by 12. Next is impulse noise. There is another image. So these are the images already given to you, and they are in the images folder. So Lena, salt and pepper noise, salt dash pepper noise .png. Okay. And over here, this is, in the case of impulse noise, there are only white dots. So there are no brown dots, no black dots over there. You will not feel any black dots. Okay, so white dots, they are somewhat shown over there. Okay, so the name is Lena Impulse, Lena-impulse-noise.jpg. So we load it and show it also. These are the noises we will be working now and also in the future class. That's why we discuss them over here. And we discuss it all for the same image so that you know the comparison. You can feel the difference. And the last noise is the Gaussian noise. Gaussian noise, maybe you think that it's like the salt and pepper, but no. It is basically the image becomes like a rough, not so neat. So everywhere the image will have patches. So here is the Gaussian noise where the image is not so smooth anymore. Okay, so these are the four types of noises that we describe. They are three types of noises. They are shown in three variables. So basically there are four variables. img1 is for original image, img2, 3 and 4, they represent the three types of noises. Clear? So this is it. Next is the filtering part. That's what we did in the last part of the lecture too. Filters we discussed. There are two main types of filters. What are they? So there are the averaging filter and the Gaussian filter. Averaging filter is also called as uniform filter or the box filter. Same name. For all three names are same. So I will show you over here the filtering process. Filtering process, how you filter the image, it is same for box filter and also it's same for Gaussian filter. So we do the filtering in three steps. Three easy steps are there. First, I show these three steps on the salt and pepper noise. First step is you define the kernel. Which kernel you want to use. So if you are using the Gaussian, steps will be same, but in step 1 you will define kernel for Gaussian. Here we are using the box filter. So we will be making a kernel like this one. Okay, so we define the kernel, and basically filtering is the process where we use these small images. So these images are basically called kernels and another name is masks. Okay, so kernel is basically like a window. As you remember, we discussed over there, it's like a window that moves over the whole big image, and it do some operation which we called as correlation. So if you remember, I gave you the example. There is a whiteboard in the class. If I want to erase the whiteboard, I will take my eraser and I will move it on the whole board slowly. So same is the process for correlation. So in the correlation, we move this small image, which is the mask or kernel, on the original actual image, and we do some operation, which was the averaging operation, if you remember. So we do this operation on the whole image. So here we see how to define this kernel, this one. There are two methods to define this kernel. So one method which is more preferred, you can say, it is to define it by you can do it sometimes manually like this. So you want to define the numbers 111 9 times, so you will define them like this. This is the first row, second row, and then the third row, and all these three rows, they are enclosed inside the outside square brackets for the matrix. When you define it, remember in the lecture I told you clearly that the matrix overall matrix value should not be greater than 1 and also not less than 1, because this matrix does not change the image. So its value should not be more than or less than 1. So here I have 9 ones, that's why I divided by 9. Clear? So overall the matrix that is created is like this. So 1 over 9 is same as 0.11. So 0.11 is repeated 9 times, 9 values. If you make the sum of all these values, it is equal to 1. Clear? Remember, what is the purpose? Why we use np.array? If you don't use np.array, what will happen? If you don't use np.array, the big problem is that the simple Python don't understand that how we can divide 9 with the value, with the whole matrix. In that case, you have to put the 9 over here inside. You cannot divide it like this. You have to divide it with each of the variables separately. So it should be 1 divided by 9, 1 divided by 9, 1 divided by 9, all of them. So this operation that you perform here, 1 by 9 for the whole matrix, this is done with the help of NumPy. So NumPy is the short for numeric Python, and it helps to do matrix operations easily. That's why it's very popular library. There is another function in NumPy to do some calculations easily. That one of them is called np.ones. So np.ones is a function which will create a matrix having all the values equal to 1. So when all the values are equal to 1, it will create a matrix of this size that is given inside. So the size of this matrix is 3 by 3. Remember, 3 comma 3 is inside small brackets. This is a single value, 3 by 3. So it will create something like this. So the same result but different values with different commands. So these commands are different but the result is same. Clear? When you are done with the first step, which was to create the kernel, define the kernel, the second step is easy, that you have done already many times. You load the noisy image, the image that is bad. So here I load first of all the salt and pepper noise. So here you see, and I show this image also. I just wanted to show this noisy image, so I show it. So I call this image as image A. So I show this image, and remember, for the kernel I also use the same notion. I said KA, which means kernel A. So I have image A which will be filtered using kernel A. Okay, so this is the image A, you have seen already, and the result of this will be stored in a variable called result A, RESA. Now the correlation that we performed in the class that I showed you graphically in the class, we moved the small kernel on the whole image. This process of correlation for the images, it is performed in the using the CV2 function called as filter 2D, two-dimensional filter. So it's doing the filtering. So filter 2D will take 3 arguments: the image, the kernel, and in between there is a constant parameter -1. We don't disturb this -1, always keep it same. And the other two are the ones that we already know, the image and the kernel. Don't change their positions. Okay, so the result is over here. The result is a little better but not so good. Okay, so you see over here the noisy image, here it's a little better. Remember, we are discussing the theory, we are improving slowly. We will go to more advanced techniques also. Clear? So these are the 3 steps. The last step was to apply the correlation function in CV2 and then display the result. So this was it. Now I can show you another kernel, another averaging or box filter kernel. So remember in the class I discussed 3 by 3 kernel is the small size. The next bigger size is 5 by 5. We always make the kernel in odd size, odd dimensions. So here the size of the filled kernel is 5 by 5 and all of them are ones. So 1, 1, 1, 1, 25 times. 5 by 5, 5 multiplied by 5 is 25. So you divide it by 25. So remember the rule is all the values of the kernel, when you sum them up, they should be equal to 1. So this is my kernel over here. I define it this time as KB, and the image B this time is the impulse noise. Okay, I don't show the image B. You can try it yourself when you are playing with these lab notes. Here I don't show the noisy image. You have already seen it above, and the result is this one. This result is also not so good, but still it's better than the original. If you want to see, original was somewhere up. Where is noisy image? This is the noisy image. Okay, the result image for the impulse noise, resulting image is blur. That is one obvious reasons. The blurring always occurs for any image. Blurring occurs, that's the normal thing, but the noisy part is gone. What was the noisy part? There were lots of white dots. They are gone now. Clear? Then I repeat the same process. This time a little faster I will go. So I repeat the same process with the Gaussian noise. So for the Gaussian noise, I will show you over here. The filter I use is the same 5 by 5 averaging filter, and applied on the Gaussian noise, it's like this. Okay, the results are not so good, but we are only for now discussing the effects of theory, what we studied. Next thing that comes after the averaging filter is the Gaussian filter. Remember, Gaussian filter is a weighted averaging filter, and over here the weights are given differently. So you cannot now use, now you can't use the command np.ones because the values are different. So first row is 1 to 1, second is 2 4 2, and the third is 1 to 1 again. Clear? This time I divide it by 16 as we discussed in the class, because the sum of all these values, sum of all these weights is 16. So then I use the salt and pepper noise, and I apply this kernel D on the image D, and the result D is shown here. So there is improvement, but little bit, not so perfect. And then I apply the same Gaussian filter now on the impulse noise. This is another result. Maybe this is not so different from the averaging filter we saw above. Finally, the Gaussian filter, I use it on the Gaussian noise. So this time you see over here the Gaussian filter and the Gaussian noise, I use it. So remember, the Gaussian filter is basically this value. The middle one, it is basically, why it is shown like this, 0.25, because remember the middle value is 4. 4 divided by 16 is 1 divided by 4. So it's 0.25. Similarly, the other values, this one is 1 over 8, and the value that is above it is 1 over 16. So this is the result over here for the Gaussian noise removed by Gaussian filter. So this was the first part. In the second part of this lab, we will improve on it, and we will try to do some more better techniques. Okay, and the assignment part for this lecture, for this lab, I will discuss in a separate video.